This is how the AI industry evaluates success. A system processes an opaque task and outputs a single numerical score. The internal computation remains hidden. Evaluating an AI agent based solely on its final output state creates a critical vulnerability. When you measure only the final destination, you have no mathematical certainty about how the system arrived there. This opacity hides severe failure modes. Behind a perfectly formatted correct answer, the agent's trajectory might contain silent infinite loops, failing tools, or retry laundering, where the model secretly exhausts multiple attempts until it stumbles into the right format. To mathematically secure an AI agent, we must verify the chronological steps it took. We cannot merely parse the final output artifact and assume the process was sound. The OpenLine protocol provides the architecture for this shift. It moves the evaluation layer away from output trust and anchors it entirely in trajectory verification. It replaces blind faith with a strict, observable stack. Every boundary crossing requires a hash-chained receipt, and state updates sit behind fail-closed barriers. True accountability requires cryptographic proof of the work performed. A successful run requires a mathematically continuous trajectory. The foundational layer of the OpenLine stack is the cryptographic hash chain. It physically locks state transitions into a strict chronological sequence. Every time an agent crosses an external boundary, sending a prompt to a model, sending its decision to a tool, or submitting output to a grader, the protocol demands a receipt. This directed acyclic graph maps the mechanism. The chain is driven by a simple function. Receipt n equals the cryptographic hash of receipt n-1, combined with the new action n. By incorporating the exact hash of the previous state into the current receipt, the protocol mathematically proves the local chronological order. The new receipt cannot exist without the exact predecessor. This sequential dependency mathematically secures the integrity of the entire trajectory. Every step, from the initial prompt anomaly to the final graded answer, is structurally bound to the steps before it. Once the chain is generated, the focus shifts to verifying it against tampering or omissions. Any mutation, deletion, or hidden retry in the sequence breaks the mathematical dependency. The equation fails, exposing the discrepancy immediately. The hash chain is enforced by the OpenLine eval airlock. This repository acts as the structural checkpoint that reads the receipts. The airlock operates on a fail-closed engineering philosophy. In an evaluation context, this means if the cryptographic proof is incomplete or missing, the system defaults to total rejection. We can see this logic applied in the repository's 7th testing scenario, the incomplete chain demo. This diagram illustrates a run where the agent publishes a successful final score, but attempts to pass through the airlock lacking the required model answer receipt. A secondary failure state occurs when the answer receipt is present, but the greater verdict receipt is missing or tampered with. In both cases, the verification function returns false. The airlock rejects the claim, even if the published output score mathematically aligns with the benchmark expectation. The absolute rule of the OpenLine protocol is simple: no chain, no batch. An incomplete mathematical sequence invalidates the claim. A benchmark score without a complete verified chain has no technical legitimacy. Beyond evaluation, trajectory verification allows us to completely rethink the agent's internal state architecture. Most software protects its state by narrowing its intake, refusing to look at complex or noisy signals. This diagram models the bipartite state. It separates signal intake from state commit, allowing the agent to process high-variance discovery without corrupting its core operating parameters. The high permeability buffer lives on the outer edge. Here, the agent freely inspects wide, unverified, and potentially hazardous signals without risking damage. To cross into the core, the data must hit the strict commit barrier. This gateway demands Boolean quorum verification, a mathematically certain consensus, before allowing any write access to the protected state. The fundamental operational rule of the immune layer is strict. Raw data never crosses the barrier. Only mathematical proof moves inward. True system robustness comes from a hardened write barrier, not from blinding the agent. You can widen the sensory intake indefinitely as long as the commit layer requires absolute proof. To stress test this strict commit barrier, the protocol requires an objective mathematical ground truth. That ground truth comes from the Ulam sequence, named for the mathematician Stanislaw Ulam. It provides a formal, infinitely scalable logic test. OpenLine utilizes the Audited Conjecture Engine, or ACE. ACE is designed to move an agent's raw, unverified anomaly into a proof-ready claim. This mathematical sorting visualization demonstrates the Ulam prefix rule constraint. A valid term must be the smallest integer uniquely expressible as the sum of two distinct earlier terms. The conjecture engine forces the AI agent to generate unverified integer candidates rapidly inside the high permeability buffer. Every single candidate is subjected to full greedy prefix rule verification. The Ulam 2-3 seed results are absolute. The agent generated a verified final proof package of 400,000 consecutive terms. It reached a final value of over 4.4 million with 0 mismatched counts. This testbed proves the core architectural claim. The engine successfully distilled hundreds of thousands of chaotic anomalies into verified mathematical claims, leaving the protected state uncorrupted. The OpenLine protocol operates on 3 structural pillars: hash chain telemetry, fail-close evaluation airlocks, and Boolean commit barriers. The protocol provides a strict, observable health stream. It functions as an infrastructure layer, leaving alignment and certainty to external verification. The preserved cryptographic evidence of an agent's trajectory is its primary output. ReceiptGate anchors raw actions to auditable proof. This paradigm rejects the press release model of AI benchmarking, where unverified top-line scores are treated as facts. A final answer is meaningless if the process cannot be audited. True accountability requires a cryptographically verified trajectory. Verify the run, do not trust the score.